Dear students, do you want to get into the fascinating world of physics? Please see this video and also subscribe to this channel.
Dear students, in this video, let us learn about an alternating current circuit which contains pure resistor, only an inductor, and only a capacitor. Now let us study about AC circuit containing pure resistor. So this is the AC circuit having only a resistor R. In this case, the voltage applied is given by the expression V is equal to V and sin omega t. And for this, let us consider a circuit which contains a pure resistor of resistance R connected across an alternating voltage source, as shown in this diagram. The instantaneous value of the alternating voltage is given by the expression V equal to V and sin omega t. An alternating current I flowing in the circuit due to this voltage develops a potential drop across R, and that is given by VR equal to IR by Ohm's law. And Kirchhoff's loop rule says that the algebraic sum of potential differences in a closed circuit is 0. For this resistive circuit, V minus VR is equal to 0. And from the equations 4.37 and 4.38, we get this equation I equal to Im sin omega t, where this Im, the maximum value of current, is given by Vm by R, where Vm is the maximum voltage and R is the resistance. And that's the peak value of alternating current in that circuit. And from the equations 4.37 and 4.39, we get that the applied voltage and the current, they are always in phase with each other in a resistive circuit like this. This means that if the voltage increases, current also increases, and if the voltage decreases, current also decreases. And if the voltage is increased in the negative side, current is also increased, and that will reach a maximum. And if it is becoming a minimum, then reaching 0, current will also become 0. This means that both the voltage and current are in phase with each other. So this is indicated in this phasor diagram 4.41, and this means that the current is always in phase with each other with the voltage. Next, we will consider an AC circuit which contains only an inductor, that is a coil here of inductance L, and that is connected to an alternating voltage source. For this, let us consider a circuit containing a pure inductor of inductance L and connected across an alternating voltage source as it's shown in this diagram. The instantaneous value of the alternating voltage is given by the expression V equal to Vm sin omega t, where this Vm is the maximum voltage, V is the instantaneous voltage. The alternating current flowing through the inductor induces a self-induced EMF or back EMF in the circuit, and the back EMF is given by the expression E equal to minus L di by dt. And by applying Kirchhoff's loop rule to a purely inductive circuit, we get these expressions di equal to Vm by L sin omega t dt. And integrating on both sides, we get this expression I equal to Vm by L omega into minus cos omega t plus constant, and here this is called as the integration constant, and that is independent of time. Since the voltage in the circuit has only the time dependent part, we can take the time independent part in the current as 0. That's the integration constant. And here this is the phasor diagram and wave diagram for AC circuit with only an inductor. So the expression for the instantaneous value of current I is given by Em sin omega t minus pi by 2, where this omega m by omega, this is Vm by omega L is given by Im, maximum value of current. That's called as the peak value of the alternating current in the circuit. From the above equations, we see that the current always lags behind the applied voltage by pi by 2 in an inductive circuit. So that is depicted in this phasor diagram here, and this is called the wave diagram. In this case, you can see that if the voltage is increased, the current will become 0 as voltage reaches the maximum value, and if the voltage reaches 0, current will become maximum, but they are lagging behind each other. So in the wave diagram also it is seen that the current always lags behind the voltage by 90 degrees. And let us see what is inductive reactance, which is shown, which is denoted by letter XL. The peak value of current Im is given by the expression Im equal to Vm by omega L. Let us compare this equation with Im equal to Vm by R from the resistive circuit. This means that the quantity omega L always plays the same role as the resistance in resistive circuit, and this is called as the inductive reactance XL, and it is measured in ohm as the same unit as resistance. So XL is given by omega L. This inductive reactance XL varies directly as the frequency, which means that it is always directly proportional to the frequency, as shown in this expression XL equal to 2 pi FL. Here F is the frequency of the alternating current, and for steady current F is equal to 0, therefore XL is equal to 0. Thus an ideal inductor offers no resistance to steady DC current. So that is what shown here. Inductor L is a closely wound helical coil, as you all know, and the steady direct current flowing through the inductance produces uniform magnetic field around it, and the magnetic flux link remains constant. Therefore, there is no self-induction and self-induced EMF, that is back EMF. Since the inductor behaves like a resistor, direct current flows through an inductor. The alternating current flowing through the inductance coil produces time-varying magnetic field, which in turn induces self-induced EMF, and this back EMF, according to Lenz's law, opposes any change in the current. And since the alternating current varies both in magnitude and direction, its flow is opposed in the inductance coil. For an ideal inductor of 0 ohmic resistance, the back EMF is equal and opposite to the applied EMF. Therefore, the inductance coil will always block AC, that alternating current. Now let us consider the next case in which the alternating current is passed through only a capacitor. That is an AC circuit which contains only a capacitor like this. So here is a capacitor which is connected to an alternating voltage source. Vm equal to Vm sin omega t. V equal to Vm sin omega t. That's the instantaneous value of the alternating voltage. And here Q is the instantaneous charge on the capacitor, and the EMF of the capacitor at that instant is Q by C. And according to Kirchhoff's loop rule, we get this equation Q equal to C Vm sin omega t. And therefore the current I is given by C Vm dA by dt of sin omega t. We can write the expression for the instantaneous value of current I as Vm by 1 by C omega sin omega t plus pi by 2, and the instantaneous value of the current is given by I equal to Im sin omega t plus pi by 2, that is Vm by 1 by C omega equal to Im. That's the peak value of the alternating current. So from these equations 4.43 and 4.4, we see that the current leads the applied voltage by pi by 2 in a capacitive circuit, and that is represented pictorially in 4.45. So here, this is the phasor diagram and wave diagram. In this case, you can see that the voltage is increased from 0 to maximum, but the current becoming 0 as the voltage reaches maximum value. Then only it starts increasing in the opposite direction, which means that the current leads the applied voltage by pi by 2. Now let us see what is capacitive reactance, that is given by Xc. The peak value of current Im is given by Im equal to Vm by 1 by omega c. Let us compare this equation with Im equal to Vm by R for a resistor circuit. And therefore, the quantity 1 by omega c plays the same role as the resistance R in the resistor circuit. And this is the resistance offered by the capacitor, and that is called as capacitive reactance Xc. And it is also measured in ohm. And the expression for that is given by Xc equal to 1 by omega c, and the capacitive reactance Xc varies inversely as the frequency. For a steady current, F equal to 0, and Xc is given by the expression 1 by omega c or 1 by 2 pi Fc. So for a steady current, F is equal to 0, therefore it will become infinity. So a capacitive circuit offers infinite resistance to the steady current, so that steady current cannot flow through the capacitor always. This we should remember. So this is the phasor diagram and wave diagram for the voltage and current in a circuit, AC circuit containing only the capacitor.